This is the SPIDAL tutorial. This tutorial will show how to use SPIDAL libraries. The first two steps of the tutorial will provide instructions on how to install all the required software on your computer. Then we will look into an example that is being done using SPIDAL libraries. The first step is to install all the required software. The three main software that you need is Java, Apache Maven and OpenMPI. This tutorial will be done on the operating system Ubuntu 16.04. In order to install Java, you need to download the Oracle JDK from the given link in the tutorial and extract it to a folder. For Apache Maven, you need to download the latest Maven release from the given link in the tutorial and extract it to a folder. Then you need to add them as environment variables. This can be done by adding these lines into your bash RC file. We will take a look at how it is done. So in this installation I already have downloaded the required software. Now we need to add these lines into the bash RC file, as you can see, and then replace this with the actual path and do the same for Maven. Now you can use the source command to make sure the changes are loaded. In order to check, you can use Java -version and -version. Next we need to install OpenMPI. To install OpenMPI, first you need to download the OpenMPI version 1.10.1 from the link given in the tutorial, then extract it. Also create a folder called build, which will be used later. Also, if your system does not have G++ installed, you need to install it. The commands given here will help you do those steps. Since my system does not have G++ installed, we will install it. The next step is to add these environment variables to the bash RC file. As you can see, I have already added those lines and added the paths to the lines. As before, we'll use the source command to make sure everything is loaded. Next, you can use this command to go into the OpenMPI directory. Then in order to build the OpenMPI, you need to execute the second command that is given in the tutorial. This may take a little while to complete. Now that command is finished, next we need to give the command make. This command will also take a little while to complete. Once that command is done, we will do a make install. This will also take a little time to complete. After that command is done, we can use the mpi run -- version command to check if everything has been installed properly. Next, we need to install the mpi jar as a Maven artifact. To do that, we need to execute this command. Now we have all the software that we need installed on our machine. For the second step of the tutorial, we need to install all the SPIDAL software that we need. First, we need to install the common library. The common library is used by almost all the other SPIDAL libraries. In order to do this, you need to first clone the Git repo of the common library. Then go into the command library. Then we need to use this tool to add the key store that is needed. This is needed because of an SSL issue in one of the dependency Maven repos. You can add any password that is 6 characters or long for this. Then it will ask if you trust the certificate. Press Y and enter. Next, in order to build the Maven library, you need to use this command. If you are doing it for the first time, it might take a little while to complete. Next we need to install DAMDS. In order to do that, we need to first clone the Git repo of the DAMDS library. DAMDS is a multidimensional scaling algorithm developed by SPIDAL libraries. This can be used to reduce dimensions of high dimensional data, as we will see in our examples. cd into the DAMDS library and execute maven install. The last software we need to install is the DAPWC library. Again, we need to clone the Git repo of the DAPWC library. Go into DAPWC and execute men install. While building DAPWC, if you get an error of some kind, please use this command again. Then use the normal men install command. To give a small introduction into DAPWC and DAMDS. First, DAMDS is a multidimensional scaling algorithm, as I mentioned before. This is a parallel implementation and can be used with very large datasets in supercomputers. For example, if you have a set of data that is in 10-dimensional space, it is hard to visualize them. So you can use DAMDS to reduce the dimensions to 3D and then visualize those 3D points. DAPWC, on the other hand, is a clustering algorithm which can be used to cluster high-dimensional data. This is also a parallel implementation and can be used with very large datasets on supercomputers. In our examples, we will look at how both of these algorithms are used in a practical manner. Next, we will look at one of the examples done using the SPIDAL libraries. We will look at the fungi gene sequence clustering algorithm. The use case of this example is based on a set of fungal gene sequence data, and we will use DA-PWC and DA-MDS to cluster and visualize the dataset. Because the complete dataset is very large, we will only use a very small subset of the data for this tutorial. To take a look at the complete dataset, there are around 7 million total sequences in the dataset. From that, the number of unique sequences is around 570,000. The number of unique sequences that appear more than once is around 170,000. So for the complete analysis, we would normally use 170,000 unique sequences. But for this tutorial, we will only be using 2,400 gene sequences. The introduction shows the steps that are needed to analyze the complete dataset. When analyzing the complete dataset, we would go through some of these steps more than once in iterations. But for this tutorial, we will only use a single iteration. So the first step is to process the raw data and find unique sequences. This is how we find the 170,000 gene sequences from the 7 million dataset. Then we need to run Smith-Waterman algorithm to generate distance metrics. Then we use DA-MDS algorithm to reduce the dimensions of the dataset to a 3D data points for visualization. As the fourth step, we use DA-PWC to generate a set of clusters. When working with the complete dataset, we only set a very small target in the first iteration, and later keep increasing the number of clusters as we go through the iterations. Then we use the results from the MDS and the DA-PWC and visualize it using a tool. For this, we use a tool called WebPlotTwist. We will see a demo of that in a little while. After visualizing the dataset, we have a better idea of the number of subclusters that are in the 8 main clusters that we generated in the first round. Then we can use DA-PWC again to generate a smaller set of clusters. We will keep iterating through these steps until we get a set of clusters that we are happy with. So here we have listed 2 visualizations from the complete dataset, which you can take a look at. So the first one shows the complete dataset after the first iteration, and it only contains 8 clusters. So as you can see, it has only 8 clusters, and you can clearly see that some clusters can be broken into many smaller clusters. The tool we are using is called WebPlotTwist, which can be used to visualize 3D data. Then after a couple of iterations, the final result has 65 clusters. This is also visualized using WebPlotTwist. In the final result, you can see that clearly all the small clusters have been identified and colored properly. For this example, we will only use about 2,400 gene sequences, so we will not get the exact result like this, but a very small subset of it. Now we will go through the steps ourselves. In order to start out this tutorial, first you need to clone this Git repo that is provided with the tutorial. I have already cloned it, that is named applications. Go into the applications folder after cloning it, and then go into the fungi gene sequence folder. In this repo, we have provided you with several files in the data directory. You can see that there is 2 files, a gene sequence file and a distance matrix. If you open up the gene sequence file, you can see that it has several gene sequences, actually 2,400 gene sequences. The next step would be to use Smith-Waterman algorithm and generate a distance matrix file. But running the Smith-Waterman algorithm for even this dataset takes a lot of time. So we have provided you with the pre-generated distance metrics file here, which is called distance metrics.bin. If you want to look at the Smith-Waterman algorithm, there is a link given in the tutorial where you can find the source code for the parallel implementation of Smith-Waterman. The next step is to use DAMDS to reduce the data to 3D points so we can visualize it. We have provided several scripts that you can use to do this. So to run MDS locally, you need to use the scripts run mds.sh file, which you can find in the scripts folder. So you can see that there is a config.properties file. If we open it up, we can see that the distance matrix has been pointed in this file, and it has information like the number of data points and maximum number of iterations in that file. This file will be used by DMDS to run the algorithm. So we can just do run MDS, which will take a little time to run. Now we can see that DAMDS has completed and it has generated a set of data files. If we open up the DAMDS points.txt, we can see a set of 3D points. This file will have data points of 2400. So next we need to visualize it. For this we will be using the tool that we showed before called WebPlotTwist. So you can easily create a new account in WebPlotTwist by going into register. So if you want, you can quickly create an account and use that to upload your files. So I have already logged in. But before you upload the files, you need to make sure that the files are in the proper format. So you can use the format.data.sh script to format your data. So just execute this command and it will format the data for you. So now you can see there's another file called DMDS points.txt.formatted. If we open that, we can see it has been formatted properly. This format is recognized by the WebPlotTwist. Then you can directly upload that file to WebPlotTwist using the upload function. Upload an artifact. Just choose the file, give a description, and you can just click upload. So for this tutorial we have already uploaded the file, which is linked here. So this is the dataset after running MDS. As you can see, there is only one cluster, so that is why everything is colored in white. But you can see there are some clusters that are visible. So we will use DAPWC to try and find the clusters that have been found in DAMDS. The next step is to use DAPWC to cluster the data. We will directly do clustering on the distance matrix that was used as before. There are several script files that are included in the tutorial that you can use for this. They are located in scripts/DAPWC. As you can see, there are several script files. So we will run this run_dapwc.sh file. before that, let's take a look at the config file. So the config file points to the distance matrix. It has a number of points and it also has a number of centers. This is the target number of clusters that we are telling the algorithm to find. So it will try to find 10 clusters. So now we will run it. This may take a little time. As you can see, now the DAPWC run has ended. So you can see here the time it took. So in my machine it took around 18 minutes to complete. So this might vary depending on your machine and your CPU speed. So it will take around 10 minutes, I guess. So next step is next we need to merge the results to get the visualization. So we have two results, one from the DAPWC which contains the clusters, and one from DAMDS which contains the data points in 3D space. So first let's take a look at the clusters. You can see a file called clusters M10 and C10. So that shows the number of clusters we specified and the number of clusters that it found. So it has found 10 clusters. If you open that up, we can see an index and a number. So this number corresponds to a cluster. You can see that there's a number for each of the 2400 data points that we used. Now in order to merge them, there is another script called merge and format.sh. We will use that to merge these two files. So if you go into the scripts folder again, you will see that merge and format.sh file. Now you can copy the command that is given to you in the tutorial. And use that to merge the results. So you can see a file called points formatted.txt. Let's open that up. So now you can see the index, the points, and then the cluster IDs of each of the data points. Like before, we will upload this file to the web.twist tool we showed earlier. So we have already uploaded one of the results to show you. So this is the results we got. So initially when you upload it, you would get a white set of data points. So then what you have to do is, there is a tab here called cluster list. When you click that, you can set a color theme. So currently I have set a custom one, but you can choose from one of these color themes, or you can directly select the color you want for each cluster. So you can see that the algorithm has properly found out each cluster that you can visually see. So there are some clusters that can be even broken down to even more small clusters, but for that we will need to go through another iteration of this process. So that concludes the SPIDAL tutorial. If you want, there is another example that is listed here. You can follow that and go through the description to follow this tutorial as well. This is based on another set of biology data called pathology image data, but it uses DAMDS and DAPWC as before.